Okay, today we're going to get into the first part of chapter 17, and before we do that we have to go back and review redox reactions because we're going to deal with cells and kind of electricity from a chemical perspective. So if we remind ourselves what a redox reaction is, it's where electrons are transferred. Okay, one or more electrons are transferred. And if we think about this from the perspective of oxidation numbers, which we're going to have to review, sodium has an oxidation number of 0. Chlorine has an oxidation number of 0. As soon as they undergo the synthesis reaction, sodium is going to have an oxidation number of +1. Chloride is going to have an oxidation number of -1. So the sodium went up from 0 to +1, and chloride went from 0 to -1, so it went down. So if we look at this from a definition standpoint, the species losing electrons is said to be oxidized. Okay, I'll just underline there. And the species gaining electrons is said to be reduced. Okay, and you also can look at that from a charge standpoint or oxidation number standpoint. And that sodium is losing an electron, its oxidation number is going up. So sodium is what is oxidized. Chloride is gaining an electron, its oxidation number is going down, so it is reduced. And also, since sodium is what is oxidized, it is causing the chlorine to be reduced, so it's also the reducing agent. And chlorine is being reduced, but it's causing sodium to be oxidized, so it's also the oxidizing agent. Okay? Now, a little bit of reminder, what can be redox? Some common reactions that we see that are redox are going to be, there we go, synthesis, decomposition, single replacement, and combustion. Almost every single one of these involve electrons being transferred in some way, shape, or form. So this is a pretty big umbrella for types of reactions to all be redox. Ones that are not redox are typically double replacements. Metathesis, double displacement, or neutralization, acid-base falls into this category, as well as precipitation reactions. Okay, those are not transferring electrons, it's simply ions rearranging, and typically products being produced that are insoluble. So that's what falls into that category. Alright, now again, we've also talked about this, but just another review for the terms. Oxidation is an increase in the oxidation state or a decrease in the number of electrons. Reduction is a decrease in the oxidation state or an increase in the number of electrons. You can get Leo Ger, and also we then add in the oxidizing agent and the reducing agent versions of that. So we simply, again, define that oxidizing agent contains the element that is reduced. I always think of it as it causes the other thing to be reduced. The reducing agent contains the element that was oxidized. It causes the other one to be reduced. And so what you end up with is Leo, put the RA on the end of it, Garoa, however you want to say it, but that's a simple way to review those. Apparently it's really important. Okay, so let's start talking electrochemistry. First thing we're going to do is talk about what are called galvanic cells. Now, and even if we think about electricity from a chemical perspective, we just have to have particles that are charged. Now, you'll hear the term galvanic cell or voltaic cell depending on your source. I believe your book uses one and Shakashira uses the other. But this is a device that essentially changes chemical energy into electrical energy that we can use. Okay? And that's the basis of it. And it uses a redox reaction because if we're going to have electricity, we need to have a flow of charged particles, and that flow of charged particles is going to come from those electrons that are being transferred. And the reducing agent, like I said, will transfer the electrons to the oxidizing agent, and if we can capture that transfer of electrons, then we can generate electricity. So oxidation, again, is the loss of electrons. Reduction is the gain of electrons. And typically the way that we see these, and we're going to do a lab that will hopefully work, where the electrons are going to travel along this wire, which is exactly what we get in electricity. So we're just setting up these two cells and allowing the electron path to be where we can measure the electricity. Okay, so if the two half reactions are combined in the same container, the electron exchange will occur directly as work is released as heat. Okay, and that's why a lot of times with electricity you have to worry about things getting overheated because the work that's being done is being transferred to heat energy. Now, to harness the energy, We want to capture it. That's why we keep each half reaction in a separate container, and so the electron transfer occurs through that wire that I was talking about. Okay, and so that wire is how we're going to capture the electricity. Now, another thing that we need to have, because this reaction is so dependent on ions and ion concentration, and we know with Le Chatelier's principle that we can force reactions to go certain ways depending on what's present, we have to somewhere have either a salt bridge or a porous disk that will allow for unrelated ions to move in order to allow for a balance of charge. Okay, and so we're just gonna, when we do these, we're gonna take some filter paper and soak it in, I think, sodium nitrate, and we're just gonna drape it across. You also can get setups that have this porous disk. It's kind of like a semi-permeable membrane that will allow those unrelated ions to move back and forth, so you don't get a big imbalance in charge. Now we have to define some things. It says which direction will the electrons flow? Okay, well they will flow from the reducing agent to the oxidizing agent. Okay, because that's our flow of electrons, depending on who's going to gain electrons and who's going to lose electrons. So what you're going to do is you're going to draw a lot of these pictures. And my recommendation to you would be to always set them up with the reducing agent. We're going to define anode here in a second on the left, the oxidizing agent on the right. Then you're going to always be able to have the electrons flowing in the same direction. It's just going to make it simpler. Okay, and just to we've got the wire here. This is a solid. Okay, you need to have some solid metal. A lot of times these are single replacement reactions. And then you've got solutions in these beakers, and then you have another solid over here. All right. Now we do have names for the locations of each of the half reaction. The anode, if this is the reducing agent, then the anode is where the oxidation reaction is going to take place. All right, and the cathode is where the oxidizing agent is and where the reduction reaction is taking place. Okay, so if you think back when we split these into our oxidation reduction half reactions, now we're kind of really applying that to a real world scenario. So anode is where your oxidation reaction is going to take place. It contains your reducing agent. The cathode is where the reduction reaction is going to take place, and it contains your oxidizing agent. Okay, then we have what's called cell potential. It's this little lowercase e here. This is the driving force on an electron to move it through the wire. So this is the force, and it's mostly due to a separation of charge that's going to allow the electrons to flow from point A to point B. It's also called electromotive force, or what's called EMF, another name for that. And the units are typically in volts, which should be familiar to us, and 1 volt is equal to 1 joule over a coulomb of charge. And even if you're not totally familiar with electricity, we know that batteries can have 9-volt batteries and stuff like that. So those are units of how much force is there.